how far the idea of computation and programs extends, but I also want to talk about a related concept real quick, which is chaos and reductionism. So someone who explained this really well is Robert Sapolsky. He's actually a Stanford biologist and has a super popular lecture on ethnology, which is animal behavior. And YouTube bombarded me with his videos and kept recommending them, and then over and over and over until finally I just gave in and I said, all right, YouTube, what do you want to show me? And then I got hooked and I watched 26 episodes of this guy's lectures on animal behavior, but one of them was about chaos and reductionism, which is super interesting. He drew upon the work of Chaos Making a New Science by James Gleick. There are systems which have periodicity. So a clock has periodicity. We can expect at 9 a.m. that in 12 hours, a clock will return to 9 p.m. We try to compress the phenomenon down to an equation or scientific theory to explain or predict the system. We can describe a line in a graph with the equation y equals mx plus b. So reductionism attempts to understand systems at lower levels than the whole to reduce variability and noise. Perhaps if we understand all the small parts, we can fully predict the whole, like reducing an organism to its genetic code. However, genes are actually an example against reductionism. There are billions of connections in the brain, but there aren't billions of genes coding for each connection. The code gives rules for a pattern, but the pattern can be perturbed by initial conditions. So each time you run the code and generate the pattern, it will turn out differently. We attempt to reduce variability and noise to find that both are features of the system which are scale-free. So it doesn't matter how big or how small you go. No matter how much we reduce and magnify, no matter how far we zoom out to study the whole, there will always be variability, noise, and mysteries remaining. Like the value of pi, the more resolution of the number we hope to have by finding a new decimal place, we can determine the next digit giving greater precision, but the value doesn't end. We can zoom in for precision endlessly. One cool example is thinking about Mandelbrot sets. Imagine a person who just wants to understand one small part of the Mandelbrot set, just a piece. You can magnify a small space, attempting to see the smallest magnification levels, but Mandelbrot set is defined based on the magnification level you look. We exist on a plane in a size that determines our magnification and level. We can gain local information, but we hit limitations by magnifying. So I think this is like the search for the meaning of life and understanding the universe. There is always more to learn. We can magnify ourselves. We can look at people on the whole person level, or we can magnify down to the smallest unit of us, a single cell. At the cellular level, we see a different yet familiar world. Cells interact with their environment, reacting to stimulus. Cells are able to self-replicate by dividing. Cells process information about themselves and their surroundings in variables of size, location, age, and time of day. Cells have some form of memory, at least genetically, about how to handle different circumstances. Cells self-regulate. Cells go against entropy, exchanging outside energy to maintain internal order. By performing these actions, cells trap and create more information than their surroundings, as we saw in Why Information Grows. Cells have a code, a program, given in the RNA and DNA of the nucleus and separately in mitochondria. DNA has symbols and a grammar. There are codes which signal when to stop reading a genetic snippet of information. DNA has jump statements, branching, control flow, essentially like an if statement in programming. But another amazing person, Joscha Bach, wow, he's incredible. As Joscha Bach puts it, cells are self-replicating Turing machines which exploit entropy gradients created by the laws of physics. So by existing, we shed bits of information, which amounts to information processing. Gosh, Joscha Bach, he also talks really fast, and you have to unpack everything he's saying very slowly. But we're going to talk about Turing machines now. So I mentioned it before, getting back to it. And the idea of Turing machines, though, is what is a computer? What is computation? This is actually a really difficult, complicated question, but Alan Turing set out to formalize these concepts. Computation is the systematic flipping of bits. A problem is computable if you can reduce it to mechanical symbol manipulation. Our universe can be seen as a computer in that the change we see is the change of information. The program the universe follows is according to the laws of nature. So there are a lot of cool examples of Turing machines, but computers are a controlled energy flow. They process and recombine information. Built from the logic gates up, computers are reasoning made tangible. Binary is represented as 0 and 1, but can also mean on, off, true, false, up, down. In school, you might raise your hand to signal you have a question. Notice that we can change the context to change the meaning of raising your arm. With one arm, we can represent 2 states. With 2 arms, we can represent 4 states, flipping all over. Here's an interesting if with this binary counter, and you can see how to represent numbers greater than 1 using binary. The bottom light orange numbers are only 0 and 1, the binary. To the right of it, on the right-hand side here, you see that the number is in base 10 and the type of counting you're used to. So we normally think of it as base 10. And you can find the number in base 10 by adding up the values in the middle column wherever there is a 1 beneath it. The top row shows the powers of 2. So there's a lot of great resources on learning binary and, just to get a sense of it. But let's think about base 10. So in base 10, 952 as an example is really 9 times 100 plus 5 times 10 plus 2. We can write the same thing as powers of 10. And we could say it like, 9 times 10 to the second plus 5 times 10 to the first plus 2 times 10 to the 0, which is 2 times 1. Because 10 to the 0 is 1, any number to the power of 0 is also equal to 1. So from the rightmost digit, we see a pattern where each number is 10 to the power of the digits starting from the right at 0. So binary is pretty much the same as that, the same as base 10 of what we're used to. But in binary, we change the base to 2. So instead of 10 to the power of whatever, it's 2 to the power from digits from the right starting at 0. 101 in binary represents 1 times 2 to the 0 power plus 0 times 2 to the 1 plus 1 times 2 to the 2, blah, 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 blah. It's 1 plus 0 plus 4, which is equal to 5. So in binary, 1, 0, 1 is equal to 5. And basically, just like in base 10, in base 2, we can do addition. And from here, we start to build up to some of the more complex arithmetic operations. But anything written in base 10 can be rewritten in binary. Most systems like your computer expect a certain length of binary digits. The term binary digit was compressed to the word bit. A byte is 8 binary numbers, bits, in sequence. Negative numbers can be represented by making the first bit 1. So 4 and negative 4 would be these long sequences. But notice that this changes the range of numbers we can express, since the leftmost bit would be 1 times 2 to the 7th, but is now a question of sign, plus or minus. We can also use binary to represent letters. Instead of 0100 mapping to 4, we can say 0100 maps to the 4th letter, D. In a similar way, we can represent anything written or spoken in terms of an alphabet translated to binary. So again, it's just we can make binary represent letters in the alphabet. But think about this. If we map one binary string of bits to one number, letter, or other idea, how many items can we represent? The ability to map is equal to the number of distinct binary sequences that can be made from a given number of binary digits, like a byte of 8 bits. Binary represents one of 2 options, so there are 2 ways to choose. At 2 bits, there are 2 ways to choose the first digit and 2 ways to choose the second bit. So 2 times 2 is 4 sequences, 4 possible mappings, and so on for n given bits. But we can map 2 to the n binary sequences. With just 32-bit sequences, we can have encoding for, 4,294,967,296 things. Using simple binary, we can represent more complex concepts. All we need is a system that understands what each bit's 1 or 0 represents in answer to a question. For a computation, the question is based on the rules of how the information is processed. How does the information grow from binary? Binary addition, as an example, gives us a new output sequence from 2 given binary strings added together. New information generated from given information. As expressively powerful as Turing machines are, they are of course limited. They function on deterministic processes, and there are problems which cannot be computed, like the well-known halting problem. Other than giving us computers, these ideas have spawned entire fields of theory. One such idea is algorithmic information theory. We can differentiate Turing machines based on the rules they follow to flip their sequence of bits. The rules are the program. This allows us to define Occam's razor in terms of programs. Occam's razor was originally used by scientists to determine which hypothesis to use in explaining observations. We can reframe this in terms of the minimum description length. So this is really cool, where the description length of a data sequence is the length of the smallest program that outputs that dataset. A program can be a hypothesis. It's how we think the data might be generated. The measure of the smallest program to produce an object, like a string of letters, is Kolmogorov complexity. Okay, so I hope this is clear. I'm going to try to re-say this again, but it's really interesting. Basically, from binary and bit flipping, we can get to computer programs, and we can describe science in a way of programs. So a hypothesis is like a program that allows you to generate a sequence of bits which maps onto data that you would see in the real world. And basically, the simplest program that you could use to generate the data that you observe, that is the minimum hypothesis, the simplest hypothesis that you can have. And so this spawned a whole interesting theory about algorithmic information theory, but Kolmogorov complexity, which is, just how can we find that proof of the smallest program to find what would generate that sequence of bits.
Thanks for watching. If you enjoyed this clip, please consider checking out the full video and the series linked in the description.